Hello, in this chapter we study theory of matrices, and today we study operations over matrices. But before we move to detail, I would like to remind you what we have learned in chapter 1. In chapter 1, we focus on the systems AX equal to B, right? And even in the very first lecture, we were talking about the equation AX equal to B, where A and B are numbers. So we have three cases, right? Like when A is 0, B is 0, when A is 0 but B is not 0, when A is not 0. And for those three cases, the solution set of this equation may be different, right? And we also know a general system of linear equation may have no solution, infinitely many solutions, or just a unique solution. Okay, and the thing is, you want to find the solution set of Ax equal to B. That is the thing, right? So in case if A is not 0, right, you can solve X equal to B over A, right? So that means you just multiply B with the inverse of A. You see, a very natural question is, can we do the same thing for this equation? So, but of course we need to consider the case. What does mean A is not 0, right? And then if A is not 0, we can solve for the X. We get A to negative 1B. So that means about inverse of A. Based on this picture, you would think about, yes, if you consider matrices, we also have different operations over matrices like numbers, addition, subtraction, right? And then multiplication. That's what we already see right here. A times X, right? Multiplication. Division, right? Division in the case that, yes, we take the inverse, right? Or we multiply with the inverse. So we need to find the inverse of a matrix if it is possible. And we use those, to solve our system of linear equation. Okay? So that is all about, this chapter. Alright, so before we move to, operations, let's talk about definition of a matrix, okay? So what is a matrix? A matrix is just an array of numbers. Let's say you have A11, A12, A13, and so on, A1n, and then A21, A22, A23, and so on, A2n. That is on the second row. And if the matrix has m rows, so I write AM1, AM2, AM3, and so on, AMN. Okay, so this is just an array of numbers. Okay, so if you pay attention, what is A11? 11 means this entry is on the first row and on the first column, right? This is the first row and this is the first column. Okay, so A21 means on the second row and in the first column. You see this? So basically, if you have some Aij in here, right? So that means Aij is on the ith row and the jth column. Alright? And sometimes they denote a matrix as A equal to Aij, where I is from where? From 1 to m, and j is from 1 to n. 1 to m means, this is just 1, 2, 3, so on and m. Okay? It's just a the notion. So that is about matrix. And in this case, the matrix has m rows and n columns. So I may talk about the size of a matrix, right? I say, yeah, this is m by n. This is the size of our matrix. So we have, m rows and n columns. All right. Now, if you just, look back, the system of linear equation, Ax equal to b right here. So when we solve such system in the matrix form, remember that we have two kinds of matrices, right? The coefficient matrix and the arithmetic matrix. Do you remember that? And the coefficient matrix, the size of the coefficient matrix in that case depends on the number of equations. So that is the number of rows, right? And the number of columns is the number of variables. So I hope you still remember that, right? So you see, we might talk about that, and then we might talk about equality of matrices. Of course, if you look at matrices as arrays of numbers, so when you are talking about equality of two matrices, they should be of the same size. Okay, so if you have two matrices A and B, if you have A and B, two matrices of the same size, A is equal to B if and only if Aij equal to Bij for any I and j. All right, so that means corresponding entries are equal. That's it. It's pretty easy. Like if you have the matrix A is 1, 2, 3, 4, right? This is 2 by 2. I prefer 1, 2, 3, 4, 5, 6, for example. And you have another matrix like 1, 2, x and y. Okay, let's say this. And A is equal to B if and only if corresponding entry 3 and x are equal and 4 and y are equal, right? So I can write in here x equal to 3 and y equal to 4. So it's pretty easy. Okay, now let's talk about addition and subtraction. So let's take these two examples, A and B. Okay, both have the same size, 2 by 2. Okay, so I might think about addition and subtraction. Again, if A and B are matrices of the same size, we may define the following matrices: A plus B, that is the matrix of Aij minus Bij. Okay, plus minus. So I write here plus minus. So that's why here we have plus minus. So that means if we have plus in here, so we have plus in here. Okay, so what does it mean? That means you just add or subtract corresponding entries, right? Add or subtract corresponding entries. Okay, so like I want to consider A minus B, but A and B, okay, let's say A minus B. So I have 1 minus 1 in here, 2 minus 2, 3 minus x, and 4 minus y. You see, and that is what? That is 0, 0, 3 minus x, and 4 minus y. That is A minus B, right? Or you can consider A plus B. You do almost the same thing. So you just add corresponding entries: 1 plus 1, 2 plus 2, 3 plus x, and 4 plus y. At the end, you get 2, 4, 3 plus x, and 4 plus y. If you compare this operation with operations over system of linear equations, you know, that is kind of, you just compile equations from two different systems, right? Like this. What is the first row, right? Suppose that this is some coefficient matrix of A of some system. You have the first row, 1, 2 are coefficients of the first equation. You have another row of coefficients, right? So what does it mean? You add two equations. So you just add the corresponding coefficients. Is that correct? So subtraction is almost the same. You see? So everything can be done, using the language of system of linear equations, right? I repeat again, right? Given that matrices are important and they have a lot of applications in all the areas of mathematics, but in this course we will focus on system of linear equations. Don't forget that. So we try to understand everything we learn on the language of system of linear equations. Agree? So from here you might think about what happens if you just add a matrix A with itself. So that means you have 2A, right? You have 2A. So what does it mean 2A? So basically, if you write it, you have the following one: Aij plus Aij, right? That is the definition of A plus A. And that is just 2 times Aij, right? And that is 2A. So that is kind of scalar multiplication. Scalar multiplication. And that happens not only for 2. If you multiply any matrix Aij with the K, which is some number in the set of real numbers, so the matrix Ka can be defined as K A I J. That means when you multiply a matrix by a number, by a scalar, you just multiply all entries of that matrix by that scalar. Okay, so this is scalar multiplication. Okay, let's consider the following. Let's simplify like, okay, let's consider another matrix A. 1, 2, 3, 4, 5, 6. This matrix has the size 2 by 3, 2 rows and 3 columns. And another matrix B, let's say -1, 0, and 3, 2, 1, and -2. Okay, this is also 2 by 3. So you can add or subtract, right? Let's compute A, 2A, okay, plus 3B. So what is 2A? 2A is 2, 4, 6, right? 8, 10, and 12. I just multiply each entries in here by 2, you see? And then plus 3B. What is 3B? I might have -3, 0, 9, 6, 3, -6. Okay? And then you add them. You get -1, you get 4, you get 15, and then you get 14, you get 13, and you get 6. You see? It's pretty easy. Or, in general form, you can write what is AA plus BB, right? Where A and B are coefficients. So that is nothing but you have the matrix Aij plus B times Bij. That's it. Okay? Now let's talk about matrix multiplication. We have a system Ax equal to B. In this case, A multiply with the x equal to b, right? So suppose that you have a11, a12, and so on, a1n, a21, a22, and so on, a2n, and am1, am2, and amn. So basically you have, n variables, right, and m equations. Multiply with x1, x2, and so on, xn. This is equal to b1, b2, and bm, right? Look at this. So if you remember, if you have a system, right, you can write the matrix form. And how can we multiply this matrix, the coefficient matrix A, with the x in here, and that is B in here? So the first equation looks like a11 with x1, right, plus a21 with x2, plus so on, plus a1n with xn. You see this? Okay, let me write it down, right? The first equation, a11 x1 plus a12 x2 plus so on, plus a1n xn equal to b1. You see? So basically, you multiply, this row with this column. Is that correct? And then you get b1. You see? Once you finish the first row, you move to the second row. You multiply the second row with this column. You get the second equation. Plus so on, plus a2n xn equal to b2. You see this? So basically, from this example, when you multiply two matrices, you have to multiply the row of the first matrix and columns of the second matrix. Does that make sense? Okay. Let's consider a very concrete example, and then we might generalize that, okay? So I have the following matrix A equal to 1, 2, 4, negative 3, 0, negative 1, and then 2, 1, 2, and matrix B is equal to 3, 2, 0, 1, negative 1, and 1. And here you have 3 by 3, and here you have 3 by 2. You want to consider the matrix A times matrix B. Okay, I will write A being here equal to 1, 2, 4, negative 3, 0, negative 1, 2, 1, 2, okay? Multiply with 3, 0, negative 1, 2, 1, and 1. If you look at this like two systems of linear equations, right? So you multiply the matrix A with this column first, with this column. So you get one column, right? And then you multiply the matrix A with this column, you get another column. That's it. So, you might think about this system, right? But you add just one more columns in here. And so at the end, you have another column in here. Does that make sense? So it really depends on, the size of the matrix B, right? The matrix B in this case, 3 by 2. So you have 3 by 3 times 3 by 2. At the end, you should get a matrix of the size 3 by 2. You should have two columns at the end. Okay? So we already know how to multiply a matrix A with each column. You see? So let's do that separately, and then we have the final answer. All right. So let's multiply the first row with this column. I have 3 with 1, Let me write in detail, okay? So I have 3 times 1 plus 2 times 0 plus 4 times -1, you see? And then the second one, I move to the second row, I get -3 times 3 plus 0 times 0 plus -1 times -1. And then I move to the third row, 2 times 3 plus 1 times 0 plus 2 times -1. That is the first column. You see, this is how we can get, how we learn system of linear equations, right, in the matrix form. All right, we finish this. We move to the second row and the second column in here. Okay, now I will multiply the matrix A with the second column. I get the following one: 1 times 2 plus 2 times 1 plus 4 times 1. Next one, -3 times 2 plus 0 times 1 plus -1 times 1. And then the last row is 2 times 2 plus 1 times 1 plus 2 times 1. Is it? So we need to simplify everything in here and then we get the answer. All right, so in the first column, I have 3, 0 and -4, that is -1, okay? -9, 0 plus 1 is -8. 6, 0 minus 2 is 4, right? That is the first column. Let's move to the second column. 1 with 2, 2, 2 and 4, we have 8, right? -6, 0, -1 is -7. 4, 1 and 2 is 7. So that's what we have when you multiply two matrices A and B. Okay? Now, let's try to find BA. BA. And we'll see what happened. So BA is what? Is 3, 0, -1, 2, 1 and 1 in here. Multiply with 1, 2 and 4, -3, 0, -1, 2, 1 and 2, right? You see, if we apply the same logic, so you have just, vector, 2 terms in here, 3 and 2, right? So there's no way to multiply with this column because you don't have enough 1 terms in here. Is that correct? So if you have this is 3 by 2 and here 3 by 3, there's no way to multiply them. That means in this case, AB is X, but BA does not as X. You see? That is interesting, right? Or in another word, we can say, yeah, the matrix multiplication is not commutative. That is the biggest difference between matrices and numbers. Okay? All right, but that is not all. From here, from this example, you might see. Okay, let's go back to this one, right? We can multiply A with B because the number of columns in A is equal to the number of rows in B. You see this? The number of columns in A is equal to the number of rows in B. So that is the main idea, right? If these two numbers are different, you cannot multiply A with B. So in general, if you have matrix A and you have matrix B in here, A is of the size M by N, right? So B should have the size N times K. So that means the number of columns in A I write here just in short, right? Columns in A should equal to the number of rows in B. And at the end, you get the matrix A and B. The size of the product is M times K. Is it okay? So don't forget that. In case, if you can see, if you count number of rows in B is different to number of columns in A. So you don't have the product of A and B. Okay? So we learn two things in this. The matrix multiplication is not commutative. Means AB exists, but that does not mean BA exists. And I'll tell you, even BA exists in some sense, right? In some cases. But BA and AB are not always equal. That is a problem. Okay? That is very interesting, I tell you. Let's do one more example with matrix multiplication. Let's say A equal to 3, 2, 1, 0. And B is -1, 1, 2, and 0. So this is 2 by 2. This is also 2 by 2. Let's find A and B. We have 3 times -1 plus 2 times 2, right? And then 1 times -1 plus 0 times 2. That is the first column. The second column, 3 times 1 plus 2 times 0. And then 1 times 1 plus 0 times 0. So you have 1 in here. And in this term, you have 3. In this term, you have -1. And in here, you have 1. That is AB. Let's find BA. In this case, BA is X, right? We'll see if they equal to AB or not. It's 1, 2, 0 in here. Multiply with 3, 2, 1, 0. And I have -1 times 3 plus 1 times 1. The second element is 2 times 3 plus 0 times 1. And then -2 times, okay, -1 times 2, okay, plus 1 times 0 and 0 times 0. So you have -3 with 1 is -2. The second right here is 6. And then from here you get -2, from here you get 0. And you can see actually these two guys are different. So even in this case, AB and BA exists, but AB is different to BA. Okay?